Hello, everyone. In this video, we are going to get started on section 5.5, where we learn about some other options for finding algebraic antiderivatives. This means we're learning some new methods for computing integrals. So to get started on our first new method that we're going to look at, let's look at example 1. So in example 1, we're asked to calculate the integral of 2 over x minus 1 times x plus 1. So notice, as is, the variables x are in the denominator of this fraction or rational integrand. We call it a rational integrand because the integrand is a rational function, meaning it's a fraction. Okay, so if those variables were in the numerator, then our method would be to multiply them out, FOIL out here, and then we could solve each part of the integral by just looking at a sum. But because we're dividing by these variables, the integrand has a very different behavior. And in order to compute an integral like this, we have to use a new method called partial fraction decomposition. So how this method works is that we're going to rewrite this integrand into two smaller fractions. So to do that, let's just focus on that integrand. So I'm going to rewrite 2 over x minus 1 times x plus 1. And our first step here is to write this fraction as two smaller fractions. They're might not, and smaller in the sense that the denominators are going to be simpler. So I want to write this as a fraction with a denominator x minus 1 plus a fraction with a denominator of x plus 1. Now recall, adding fractions, we can't just split up the denominator like this. When we add fractions, we don't just add up or multiply denominators. So I'm going to leave the numerator as a and b. I don't know what a and b are that make this equation true. So let's do some algebra to find what a and b need to be. So in order to do this, I need to solve for a and b. Right now, a and b are involved in these fractions with denominators. So the first thing I want to do is try to simplify this out by canceling out these denominators. So to do that, I need to multiply both sides of my equation by the denominators. So I'll multiply by x minus 1, so that when I multiply in on the right-hand side, my denominator here cancels, and I'll be left with b times x minus 1. We'll do that in a little bit more detail in a second. Now I need to do it to the left-hand side also. So x minus 1 on the left-hand side. And then I also need to multiply both sides by x plus 1 to get that denominator of b to cancel. So then also multiply here by x plus 1. Okay, so now let's see what happens with the algebra. So on the left-hand side, this entire x plus 1 times x minus 1 cancels with my denominator. And on the right-hand side, when I multiply this product in, what will I be left with? Well, when I multiply by a over x minus 1, the x minus 1s will cancel, but I'll be left with an x plus 1 in the numerator. So this will become a times x plus 1. And now in the second term, when I multiply through, the x plus 1 will cancel in the denominator. And in the numerator, I'll be left with b times x minus 1. And then on the left-hand side, because the denominator canceled out, I just get a 2. Okay, so let's keep massaging this equation a little bit more in order to solve for a and b. So let's multiply out that right-hand side. So when I do that, I'm going to multiply a into both terms and then b into both terms in parentheses. So that becomes ax plus a plus bx minus b. Now, again, all this is equal to 2. So now what I want to do is combine like terms. So what are like terms here? Well, a like term is a term that has a same power of x. So ax and bx are like terms. So I could write ax plus bx. And then just a and negative b, those are both like terms. They're just constants. So then I have plus a minus b. So again, all this is equal to 2. And so how do I combine these terms? Well, I can factor out an x from this first sum. So that would leave me with a plus b times x. And then in my second term, I just have a constant a minus b. So that's equal to 2. So now how is this right-hand side going to be equal to a constant? Well, notice the right-hand side has a term with x. The left-hand side doesn't. This means what's really going on in the left-hand side is that we have a 0 groups of x's. So what does that mean? That means that a plus b must equal 0 and a minus b must equal 2. So this gives us 2 different equations. This gives us that 0, I'm going to use the same colors here to keep track, 0 equals a plus b, and 2 equals a minus b. And so now let's just take a pause and see what we've come up with. We've come up with 2 new equations with 2 unknowns. So this means we can use these 2 equations together to find both a and b. So how are we going to do that? Well, in this first term, we can solve for a or b. So let's solve for a. So this means 0 equals a plus b, that I can subtract b from both sides. And I get that a is equal to negative b. So now I can substitute a equals negative b into my second equation. So what does that look like? That looks like 2 equals, so now a becomes negative b, so I have negative b minus b, which equals negative 2b. So this means that 2 is equal to negative 2b. So to solve for b, I divide both sides by negative 2. So on the left-hand side, I get negative 1 equals b. And so now how do we find a? Well, now we can plug in what b is up into this lovely equation where a is solved for in terms of b. So that means that a is equal to negative b. Well, b is equal to negative 1. So that means a is equal to negative 1, which is positive 1. So now I have what a and b need to be in order for our original equation to be true. So let's write that out here. So this means doing all of this work, that 2 over x minus 1 times x plus 1 is equal to 1 over x minus 1 plus negative 1 over x plus 1. So this means we can rewrite the integrand that we started with that involved this big denominator as 2 smaller fractions. So let's set up that integral. So I'm going to come down here to give myself a little bit more room. So the integral that we're looking at is equal to the integral of 1 over x minus 1 plus negative 1 over x plus 1. So why did we do all this work? Well, my claim is that this integral is solvable now using the techniques that we already know. So what would that look like? Well, we can split up this integral into each of the fractions. So this becomes the integral of 1 over x minus 1 dx plus the integral of negative 1 over x plus 1 dx. And just to simplify things, I always like to bring my negative outside right away so I just don't have to deal with it. So it's going to be negative the integral of 1 over x plus 1. So now what we're dealing here is just going to be a simple u sub. So let's look at how that would happen, how that would work. So on our first integral, if we let u equal x minus 1, we see then that du with respect to x is just going to be 1, which means that du is equal to dx. So then when I make that substitution, this integral becomes the integral of 1 over u du, which we know is equal to the antiderivative is just the ln of absolute value of u. So then when I substitute back in for x, I get the ln of x minus 1. So now following that integral on the right-hand side, we do the exact same process, but now we have u, maybe I'll use u bar is equal to x plus 1. We see that the du is equal to dx. So that gives us the integral again of 1 over u du, which then is the ln of u, which is equal to, now when we substitute back in for x, the ln of x plus 1, and we're subtracting. And so now including that constant c, we get our final solution. So the antiderivative of this original integral just becomes the ln of the absolute value of x minus 1 minus the ln of the absolute value of x plus 1 plus c. So though it took us some work to find this fraction decomposition, once we did that, then now just using two different fractions, the integral was super straightforward just to compute the antiderivative of. All right, great work working through this video. Please rewatch any parts again. Make sure you understand all of the steps that we're using in this method. And in the next videos, we'll get some more practice using this method, as well as discuss why we originally took this approach of finding the fraction decomposition. Thanks so much. See you next time.